Hi everyone, we are talking about the fast Fourier transform and this is the second part. So if you haven't checked out the first part, you should, because that is a prerequisite to understand what's happening here. We are talking about two polynomials that we have, a and b, and they are being represented as a of 0 plus a of 1x plus a of 2x square, so on and so forth. Now our simple multiplication technique of order n square is not good enough. So we are thinking about trying some new ideas to multiply these two polynomials faster. That's our aim, to multiply two polynomials fast. So one of the ideas that we got was to actually take these two polynomials, plot points for them, which is something like taking a of 1 and plotting that on the graph on the y-axis. And because x is equal to 1 here, you take the value of a of 1 here and plot that. And similarly, you plot 2n plus 1 points for a and 2n plus 1 points for b. And what you'll end up with is a graph with lots of points. But the important thing here is that the simple multiplication now to get c of x is an order 1 operation. You just take the two values, multiply them, and you have c of x. And what can you do? You can plot that also on the graph. So you see that we had a graph with the a of x and b of x points. We'll have a graph of the c of x points, and using some maths and using basically the inverse DFT, we can get back the polynomial c, which would have also been possible by multiplying these two polynomials, but it's an inefficient operation. So we are seeing that there is something efficient here, order n, because you have 2n plus 1 points and you need to multiply all the points to get the c of x's that you want. So this entire operation will be order n, the multiplication, while this is order n square. So if this operation DFT and this operation inverse DFT can be made efficient, more efficient at least than n square, then we are well off. Then we have actually improved on the fastest multiplication that we know about. Alright, that's a good starting place. Now to understand what I mean by taking a of x and b of x and then multiplying it to get c of x, let's take an example polynomial. Let's say you have a of x equal to 30 plus 21x and b of x is equal to 1 plus 3x plus 2x square. Alright, so essentially what you have is a also as 0x square over here. Okay, two polynomials which are you need to multiply. C of x will come up in the end. So what does c of x evaluate to? You have 42x square plus this is 60x square, and these two will form 63. So 123x square plus what do you have here? So x square is taken care of. What about the x is? So this becomes 90x and this becomes 21. So that is 111x. That's lucky Nelson. And what about these two? That's 30. Yeah. Let's just confirm this. And how are we going to confirm it? Take a1. So we need to substitute the value of x as 1. What do we get now? We get 51 as a1. We get b1 as 6. Okay. And c1 should be 51 into 6, that is 306. This should be 306, but let's just confirm that over here. 42 plus 123 plus 111 plus 30 gives you 6 over here, gives you 4 plus 2, 6 plus, yeah. I can't believe I got the calculation right. Oh, it's not carry of 3, for God's sake. It's 3. 306 even over here. So you're seeing that this polynomial can be evaluated for this particular point. This polynomial can be evaluated using just these two values at their respective points. So that is exactly what we are doing. We are trying to find out n points, take those values, compute c of x for those values, and then using those 2n plus 1 points, we are going to be getting back the original polynomial. So if you remember the original question, we had q queries. And for each query, we need, using the Horner's rule, if we have this evaluated, we need order n time. So that would be Qn total time plus whatever we need to actually evaluate this. So that is n square. Okay. Now we'll need, for each query we'll still need order n time. So there's no improvement there. Qn time. But actually evaluating this could be sped up using DFT and inverse DFT. So we'll see what complexity is there. Let's call it K. Yeah. This K should be better than n square. That's all that we want. Okay. So let's get to it. Okay, a quick side note on the Horner's rule. We have been talking that it can evaluate a polynomial in order n time. So how does it do that? It takes a polynomial and instead of going like this, the 2 plus 13 into x, which is 2 operations here, 16 into x square, 3 operations there because you have 3 multiplications and 4 operations and so on. So that would be 1 plus 2 plus 3 plus so on and so forth up to order n, which is n operations, which in total would be sum of first n natural numbers, n square operations. You could use fast exponentiation, but let's not get into that. The simple Horner's rule does the job. Take this term 12 and multiply it by x. Now add 16 to it. So we are taking the last two terms, we are putting them together but removing the common term over there, x square. Okay. Now you multiply this by x and add the previous term 13 over here. Now you take the entire thing and you multiply by x and then you add 2 here. So what do you get essentially? You get this term multiplied by x, which would be 12x square. I'm just focusing on this term over here. This becomes 12x square and then that is multiplied, added to 13 and then multiplied by x, which becomes x cubed. And you can see that this is equivalent to this. Okay, but in terms of computation, you need what? 2 operations over here? No, 1 operation here. 1 operation here and 1 addition, so that is 2. Then you need 1 more, that is 3. Then you need 1 more, which is 4 up to this plus. Then you need another multiplication, which is 5, and the final addition, which is 6 operations in total. How many did you need? Otherwise, you needed for 4. Yeah, 4 required 4 into 5 by 2, which is 10 operations. So this was n square, and this is order n. And so always use the Horner's rule when you are evaluating a polynomial. Okay. Alright, so we have our strategy. We know that we need 2n plus 1 points for both a and b to be plotted on this graph, and then we'll get our c of x. But the thing is, if you choose any point, any random 2n plus 1 points, then computing those points will be difficult, because for every point, that is 2n plus 1 points for both a and b, so that is into 2 over here, you need to compute the value of a and b at that point, at that x. So computing the value just using the Horner's rule would be order n. So that's n computations, and that in turn gives you n square computations. Alright, so you would get the points, and after that you could do everything, but the problem is this is n square itself, so why not go for the brute force algo? And over here we'll be doing something very clever. We'll be choosing the points in such a way that you can talk about your current point using the previous points that you have evaluated. Alright, and from there you can probably bring down the complexity from order n to something smaller. So let's see how we can choose those points smartly. So to understand this topic well, you need to know a little bit about complex numbers. So complex numbers, every complex number can be represented on this plane x and y, and you have everything on the y-axis being imaginary and everything on the x-axis being real. So real and imaginary, but basically what I can see from this is that those two quantities cannot mingle with each other. Okay, they can actually, but yeah, we'll see that they don't mingle with each other when you're adding them. 6 plus 3i plus 2 plus 4i, then you can take the quantities with I separately and add them up, 7i, and here you have 8. Alright, so that's what complex numbers are. Two quantities in a single number. For now, let's think of them that way. What do we have here then? Every complex number can be shown as a vector from 0, 0 to whatever point it is pointing at. So x plus iy would be the point x, y. And in this example, we have 1 as our x and I, in fact not I, it is 1 as our y. So you would have 1 plus I as your complex number, this vector. Okay, and there are some really interesting properties with complex numbers. So what happens when you want to multiply two complex numbers? Here's where you need to think of these as vectors having some angle with the x-axis. Okay, so let's say y has angle theta 1 and x has angle theta 2 with the x-axis, and they have lengths of, let's say the length is mod x and mod y. What will happen then is that the result of these two, when you multiply x into y, you'll get a complex number with length equal to mod x and mod y. So the lengths of the two are multiplied, that's sensible. And the angle from the x-axis is added up. So theta 1 plus theta 2 is what you get over here. That's the resultant. And remember, we are trying to calculate 2n plus 1 points to get our resultant polynomial. So, and using this property, we can find out 2n plus 1 points efficiently, because we'll be using the property of angle addition when we are multiplying two complex numbers. Okay, to make our life simpler, we'll be choosing x and y having length 1, because we won't be needing this property. Okay. So our result will always be theta 1 plus theta 2, and because x and y are 1, this will be a unit vector. So firstly, let me apologize for this drawing. It's pretty terrible, but this is supposed to be a circle of unit length on the complex plane. So every point that you see here has magnitude 1. And so these points, this is equal to 1. It's on the real axis. This is minus 1. This is plus I. It's on the imaginary axis. And this is minus I. And you see there are other points also that I've drawn. But any point on this unit circle will have magnitude 1. And you can get that point using two other points from this circle. So like we said, if those 2 points have theta 1 and theta 2, and your result should be theta, then you can choose theta 1 and theta 2 appropriately and get this point. Okay. Now going by the principle that we need to make our lives simpler, we'll be choosing these points, these thetas, very cleverly. We'll be choosing the nth roots of I. Why is that? Because we said that we don't want to deal with magnitudes, we don't want to deal with the lengths of the two complex numbers. These will be 1. So that's the reason why we are choosing 1. And the other reason why we are choosing the nth root will be clear right now. But if you see this, what is the square root of 1? Plus 1 and minus 1. What is the fourth root of 1? That would be these two numbers and square root of plus 1 and square root of minus 1. So square root of plus 1 will give you these two numbers, so that is redundant. And square root of minus 1 is equal to square root of I square, which is equal to plus I and minus I. So these four terms, 1, 2, 3, 4, give you the fourth roots of I. But calculating the nth root of 1 is quite complicated, so we'll be using this trick. We'll be representing our complex number as e raised to power I theta. Okay, this is one way that you can represent it. In fact, there is a r which tells you the radius it is making from the origin, but for us r is equal to 1, unit circle. So fine, we got rid of this. E raised to power I theta is what we have, where of course theta represents the angle it is making from the x-axis. So finally, we have the points that we need. We want to plot a of x and b of x. Well, x will be complex numbers, which will be the nth roots of unity. And we are using this notation e raised to power I theta. So, because they are the nth roots of unity, you'll be taking this circle, which is the unity circle, and you have 360 degrees to play with, but you need n points. So, you need 360 by n to be the angles by which you're jumping. So, this is equal to 2 pi radians by n. So therefore, the first point that you'll be going to is e raised to power 2 pi I by n. I is just because it's a complex number, yeah. So e raised to power 2 pi I by n using this notation. And you need n points. So you take a counter k which goes from 0 to n minus 1, and the points that you'll be choosing for a of x and b of x now is w raised to power k. So w is equal to this quantity, and w raised to power k is nothing but cos of 2 pi k by n plus I sine of 2 pi k by n. Why? Because we said that the angles are added up. The angles are added up as you multiply two complex numbers. So whenever you are adding another w of n to this, which would be w n k plus 1, this would turn into cos 2 pi k plus 1 by n, and I sine 2 pi brackets k plus 1 into n by n actually. So we have the points. Why are these so special? Let's find out some properties about these points. The first property here is that if you have the x into nth root of 1 and that is raised to x into k, then that is equivalent to the nth root raised to power k. Okay, just a simple property, I'll just prove this. You have this value, so that is cos of, what is that? 2 pi k x I by xn, okay, plus I, no, there's no I here, sorry, I sine 2 pi k x by n, and x here. What comes up? You take x and x which are common and you cancel them out. Take x and x which are common and you cancel them out. What does this come out to be? Just e raised to power, what, 2 pi k I by n, and that's exactly what this is. You know, the nth root of unity raised to power k. So yeah, the x into nth root raised to power x into k is the same as the nth root raised to power k. Okay, that's the first important property, and this is called, if you read Corman, the cancellation lemma. And the other interesting property is that if you have the nth root raised to power k plus n by 2 and you whole square that, okay, why am I saying n by 2 instead of just multiplying this term into 2? Because n has to be even for this to work. Okay, if n is even, then this property can be applied. Nth root raised to power k plus n by 2, the whole squared, is equal to the nth root raised to power k, the whole squared. This term whole squared. What's this? Well, let's go from LHS itself. So let's show this as cos of, what is it, k plus n by 2 into 2 pi. So this thing is over here by n. The whole square is actually just going to be multiplying the exponent into 2. So this entire thing can be multiplied by 2 plus I sine the exact same thing. So I'll just call it theta. Okay, this term evaluates to what? 4 pi k plus 4 pi n by 2 upon n. Now this becomes 2 pi because of the cancellation, numerator and denominator. This becomes 4 pi k by n, and there's a by n here, but this cancelled out of the numerator, so this is what we have, plus I sine theta. What do we get? 2 pi plus whatever, so we get cos of whatever, because 2 pi rotation is going to take you all the way around the circle and back where you were, and then you're adding this term. So this term can be ignored because it's not making any difference to our result. So we just get rid of that, and that is equal to this term. And I sine, again, the 2 pi can be ignored because sine theta also reboots after every 2 pi. So this is what we have, and that is equal to e raised to power I, theta is 4 pi k by n. So 4 pi k by n, which in turn is equal to e raised to the power 2 pi k by n the whole square. Now this term is this term, which is the nth root raised to the power k the whole square, and we were talking about something over here. So that's exactly what we have. Okay, two interesting properties proved. Now this video is getting a little long, so in the next video we'll see how we can use these properties and then basically plug in the points into the polynomials to get the fast Fourier transform. Okay, so stay tuned. I'll see you next time.